have seen like okay how to there are certain equilibrium reactions, industrially challenging, because if we want to have more product, then the issue is, we need to supply more amount of we need to supply some extra reaction conditions. So see here actually the equilibrium. See, let's take the example of N2 plus 3H2. It is actually 2NH3, right? So see, if you want to have more amount of ammonia, usually in this usual cases, what will happen? N2 plus 3H2 combines together 2NH3, and vice versa, right? And vice versa. So if you want to have more ammonia, actually you have to disturb the equilibrium so that more amount of ammonia will be forming. So the disturbance should be happening in such a way that more ammonia shall be forming. See, there is one particular principle that deals with the equilibrium enthalpy. So that principle is called Chateler principle. Please remember, actually Chateler principle. Okay, so this is called a Chateler principle. See, this is the concept is very simple. So you know this seesaw, right? Seesaw. Think that two people are sitting. Okay. So if they are on the equal weight, then the seesaw will not be moving. So it will be actually in a same position. But think that in the same seesaw. So if you are applying more pressure here, okay, if you are applying more pressure here, then this, do you know what shall happen? This seesaw, it will be in this side. So if you are applying more pressure here, then actually seesaw will be on this side. I mean, like it is shifting towards in this side, right? So normally what shall be the cause is, what shall be the thing is, okay, if it is think that this seesaw is shifting in this way, okay, then what we can do is actually we can apply some equal amount of pressure so that seesaw will be in the normal condition. Okay, so this is what something this Chateler principle is saying. See, I can explain you in a little more better way. A is giving B. Okay, think that this is an equilibrium. If you are disturbing here, then from this opposite end, okay, opposite end, some force will act against this. I mean, like so for opposite end, some force will be acting against this, so that again the equilibrium will be restored. So equilibrium will be in the same way. Okay, and yeah. So now we can see like in a little more better way, like how these some situations we are applying. You can check the case of this particular this reaction itself. Ammonia production itself. About this reaction. Actually, this is it is actually negative. It is actually exothermic reaction. Okay, exothermic reaction. So, so the exothermic reactions actually, do you know how it happens is, when this reaction is happening, heat is getting liberated, heat will be going outside the atmosphere. Okay, so here you think in this way. See, now we can see like what is the effect of temperature. See, for that, as I have seen N2 plus 3H2, this is actually giving 2NH3. So, always the reactions having some effect with the temperature, right? The reaction rate will be, reaction speed will be increasing, or sometimes in extreme cases, the reaction speed will be decreasing. Do you know one thing? Actually, this reaction actually, as I told you before, it's actually negative. The reaction enthalpy is negative, so it is actually nothing but it is an exothermic reaction. In the case of exothermic reaction, you can think in this way. See, when this reaction, suppose this reaction is happening here. Okay, in this reaction, in this chamber, it is releasing actually heat. Okay, so this reaction releases heat. Okay. Okay, this reaction is releasing heat. It is still goes on liberating heat. So you think that this reaction does not want heat. Already the system have heat, it is throwing out. So again, if you are supplying heat, do you know what will happen? So again, whatever the heat you are supplying, that heat also will go out of the system. That heat also will come out. So this reaction does not want heat because it is exothermic reaction. Okay. Do you know, if you are supplying heat into this type of reaction, because this reaction happens with the liberation of heat, it is releasing heat. So if you are if you are supplying heat to this reaction, okay, do you know what will happen? So actually the product formation is favored by the release of heat. So if you are again supplying heat, this reaction will be shifting towards, the equilibrium will be shifting towards the reactant side. The more decomposition will happen than the product formation. The more and more, okay, more and more ammonia will be decomposing, okay, more and more ammonia will be decomposing, and it is actually going to form nitrogen and hydrogen. Okay, so that is actually the case. And so here one thing you have to know, that is if you supply excess amount of heat, product formation will not happen. Instead, decomposition only will be happening. Here one more thing is, what the principle you need to know is, okay, so here if you want more product, okay, see, like if you want more product is actually ammonia. If you want more product, you can decrease the temperature. Now the pressure. See the pressure, how it is affecting. Let's see how it is going to affect the equilibrium. Okay, so you can consider N2 plus 3H2 gives 2NH3. So here you can, this is a gas, and all the 1R gases including ammonia, right? So if you see the reactant side, how many gases are there in a reaction? 1 plus 3. So total 1 plus 3, it is going to be 4 moles of gases, right? But here, 2 moles of gases. So you know very well, suppose you think in this way, something we are pressurizing, okay, you know, like something we are pressurizing, or like we are squeezing the gas molecules. Suppose here more amount of gas molecules are there, okay, here more amount of gas molecules are there. If I am if we are applying some pressure, these gas molecules, think that this is a balloon. If I am applying some pressure, this this will be shifting towards, these gas molecules will be shifting towards there is the region where there is a low pressure. Okay, so it will shift from a region of high pressure to low pressure. Okay, so what I am trying to tell you is, in these type of reactions, if I am applying pressure, this equilibrium will be shifting more towards the product side, because where there is a less number of molecules, okay, less number of gaseous molecules, the reaction will shift towards that side. So in this reaction, the less number of gas molecules are in the product side, that is in the side of ammonia. So the reaction will shift towards product side. So increasing the pressure, is proportional to product formation in this reaction, in the reaction of ammonia. But remember one thing, in some cases, like not all the cases, it will shift in the product side. Some cases we can check, say I am writing a general reaction, 2A is equal to 3B. Think that all are gases. If you are increasing the pressure now, then here actually 2 moles of gases are there. Here actually 3 moles of gases are there. So the reaction will shift towards the reactant side. I mean, the reaction will be shifting more towards the reactant side. Okay. So if you increase the pressure, like the reaction, it is going to shift in the, because here less number of gas molecules are there. Whichever the side the number of gas molecules are less, to that side the reaction will be shifting. Okay. So this is the case of equilibrium and how the pressure is influencing the equilibrium reactions. Done? Okay. Now we need to check the role of catalyst. Okay. So regarding this ammonia formation, we already said it, regarding the temperature we should bring down. We should decrease the temperature, then the reaction will be moving forward. Regarding the pressure, we should increase. If you increase the pressure, the reaction will be going more towards the product side, right? Yep. Now we need to check the role of catalyst, how the catalyst is influencing the rate of the reaction. Okay, we are going to check that. We know very well how the catalyst is functioning. See, what is it, and we know very well what is a catalyst also. See, a catalyst generally a catalyst is, for example, like A reaction, A, this is A is converting into B. So, if you add a catalyst, let it be X, the speed of the reaction, the rate of the reaction, it is increasing. Like, a lot of amount of product will be forming. For example, in normal cases, okay, for example, in normal cases, 10 ton is producing. Okay, 10 ton is producing. If you add a catalyst, we can approximate, we can add approximate, it shall be producing 20 ton. So more amount of product will form. So product formation, it shall increases when we are adding a catalyst. The role of the catalyst is to increase the speed of the reaction, right? In case of an equilibrium reaction, for example, A is again, we can consider A is converting into B, and provided this reaction is in equilibrium. Think that I have added a catalyst X. In that case, the reaction will go in the forward direction, also the reaction will go in the backward direction, right? So this, what the X will do is, X will increase the speed of the forward direction, okay? So it increases the speed in right of forward direction. At the same time, in the same way, it increases the rate of backward reaction also. So it increases the forward direction, it increases the backward reaction also. In the same time, it will increases. Okay. So this is the case of catalyst. This is the role of catalyst, in the equilibrium reactions. So then there is a problem. How we are going to increase the yield of B? Because the same way increasing and decreasing is happening. How we can increase the speed of how we can increase the yield of B? How we can increase the yield of product? Here is a thing I told you in the beginning. If we are not letting this reaction to be in equilibrium, okay, then actually what is the thing? If you are not letting the reaction to be in equilibrium, then the thing is, then more amount of product will form, right? So if A is keep on forming B, think that this is not in equilibrium. This is not at all in equilibrium, then more amount of product will form. More amount of B shall be forming, right? So this is the case of, this is how we can increase the rate of B. Okay, let's consider N2 plus 3H2. It is actually giving 2 NH3, ammonia formation. So, in this reaction, the ammonia is a gas, but it is a very easily liquefiable gas. Easily you can liquefy. If you cool it, it will liquefy. And if we are liquefying, this ammonia will remove from the scene. Okay. So, if we are keep on removing the product, as soon as it is forming, we are keep on removing the product, then what shall happen is N2 plus 3H2 this reaction only goes in the forward direction. The backward reaction will not happen. It is not going to happen. So the easiest and best way is remove the product as soon as it is forming, and we should add a catalyst. Guys, please remember, in the ammonia formation, iron is the catalyst. We can specifically call it is a spongy iron. Spongy iron is the catalyst in the ammonia formation, right? Yes. So now if we are summarizing the things, okay, in the ammonia formation, so one way we can increase the rate of the reaction is decreasing the temperature, but not below a level, decreasing temperature. And next is adding a catalyst. Okay. Third one is what we can do is increasing the pressure. Okay. So these are the three best ways we can increase the yield of ammonia formation. Okay. Of course, this is not a universal thing for all equilibrium reactions. It depends on the conditions and depends on the equilibrium reactions. These things it is going to change. It is going to change. Some reactions you have to decrease the pressure. Some reactions you have to decrease the temperature. In that reaction, increase the temperature. In that case only the reaction will be moving more towards the product side. Okay. So we need to work. We need to carefully, experimentally we need to work and optimize. Those experimental data we have to transfer to the industry so that the yield will be more. So remember, in a industry, time is money. Okay. More amount of product is forming, that gives the more output, more product. So whatever we do in the laboratory scale, we have to pilot, we have to scale it up and see how that is affecting, and we have to check how much efficiently that is happening. Okay. So guys, remember, many of the industries, many of the chemical industries, still they are starving. They are looking for the excellent chemistry people, to work for their industrial problems. So chemistry is, of course, it is an amazing subject, but and also there are many catalysts, a very diversified catalyst, electrocatalyst, heterogeneous catalyst, there are a lot of photocatalyst, lot of variety of catalysis is also going on. So hopefully you like this session. Okay, thank you.